At the end of this section, you'll be able to describe the general purpose and layout of the electrical system. Identify and locate the components of the electrical system. Describe the layout of the electrical system. Identify its subsystems and interfaces. Explain the operation of the electrical system main components. Describe the different power sources. Identify and explain the controls associated with the electrical system. Identify and explain the indications and annunciators associated with the electrical system. To understand the electrical system, you have to look well beyond the surface. Several panels are provided for control and indication of the different voltages available. These voltages are distributed via buses to equipment operating in the background. Together, these panels and buses compose the electrical network. We'll break these schematics down into comprehensive logical pieces in the following lessons, and you'll be able to join them together again at the end of the electrical chapter. This is what the basic logics of the electrical system look like. Now let's get started on the details of the various systems. For all the numerous consumers, the aircraft provides a supply of electrical power in the form of 28-volt direct current, DC. 2 engine-driven starter generators provide this voltage. In case they fail, 2 batteries sustain DC emergency power. 26-volt and 115-volt constant frequency alternating current, AC. AC consumers receive their electrical power from 2 main channels. Each is fed from a DC generation via an inverter. 115-volt wild frequency alternating current, AC wild. AC wild frequency is provided independently from the AC constant frequency power by 2 propeller-driven generators. The AC wild generators can also supply the direct current electrical system through a transformer rectifier unit, short TRU. DC and AC wild external power from ground power units. The aircraft can be provided with DC and AC wild electrical power via 2 separate ground power connections. For all the systems that are electrically supplied, circuit breakers provide protection from damage caused by overload or short circuit. These circuit breakers are located behind the first officer's seat as part of the electric rack and adjacent to the overhead panel. Their normal position is in, and if a malfunction occurs, they pop out to open the respective circuit, thus indicating which system is affected. All circuit breakers can also be manually pulled out at any time, thus isolating the respective electrical circuit. Some specific circuit breakers, such as the ground handling bus circuits, are fitted with plastic rings to enable the crew to quickly identify them as ones that have to be manipulated during normal operation. Based on experience, the following recommendations were published by EASA in a Safety Information Bulletin and should therefore be applied when a circuit breaker trips. If a circuit breaker trips in flight, it should not be reset by pushing it in again unless the affected system is deemed necessary for the safe continuation of the flight and landing. In any case, the crew should attempt only one reset. On ground, if coordinated with the maintenance technicians and if the cause for the tripped circuit breaker is identified, you're allowed to perform the reset of a circuit breaker. In general, when a circuit breaker trips during aircraft operation, A thorough investigation, including a visual inspection of the affected aircraft systems, electrical wiring, and the cable harnesses, should subsequently be performed. Under normal operating conditions, 28-volt DC is provided by two starter generators, one attached to each engine accessory gearbox. We'll find out more about them later. On ground, this voltage can alternatively be served by a ground external power unit via the DC ground connector on the right side of the fuselage, just rear of the aircraft nose. We'll look at this again in a separate chapter of the electrical system. The main battery, the emergency battery, and the TRU provide DC emergency supply in case the two DC generators are lost. The main battery, on ground, also provides starting autonomy. When the flight crew members enter the aircraft, the batteries are the only electrical power source available to the flight crew, as no engine is running and no ground external power is connected. First, let's discuss the batteries. If the aircraft is on ground with no engine running and no ground external power unit available, or the aircraft is in flight and both DC generators are lost, 24-volt DC is provided by two NiCad batteries. You'll find them in the base of the electronic rack. The two batteries differ in the following properties and functions. The 43 amp-hour main battery serves primarily to ensure emergency power supply, including propeller feathering, and also for starting autonomy in flight and on ground in case no ground external power is available. The primary duty of the 15 amp-hour emergency battery is emergency power supply even when the charge of the main battery is completely exploited. The battery also avoids power transients on critical equipment during engine starts. Note, the battery's capacity allows a maximum of 30 minutes of safe flight and landing. In upcoming lessons, we'll look more closely at the buses that are supplied by the batteries if the generators fail. The batteries are monitored by the MFC system, which connects the respective battery to the associated DC bus for charging, analyzes the charge current and/or associated DC bus voltage so as to prevent an abnormal battery operating condition or thermal runaway. As is generally valid for batteries, the time of usage of the aircraft batteries on ground should be kept to a minimum to preserve their longevity. Weak batteries may result from keeping the batteries switched on while refueling is performed, operating the cargo door repeatedly, using the minimum cabin lighting extensively. If during ground operations, ground external power supply is not available and hotel mode is not used. A single TRU, powered by the AC Wild Bus 2, is installed to conserve the batteries in case both DC generators fail. In this emergency situation, the AC Wild electrical system through the TRU ensures that the DC emergency bus, DC essential bus, DC standby bus, and the AC standby buses remain energized without any time limit. Note that the TRU has to be manually connected to the AC Wild Bus 2 by selecting on the TRU push button on the main electrical power panel. As you may already have guessed from their name, the starter generators are designed to work in two different modes, either as starters or as generators. Let's begin with their function as starters. When an engine starts, the respective starter generator is either connected to the aircraft main battery, the ground external power unit, or the main battery and the operating generator of the other engine. This happens only on ground for a cross-start purpose. The cross-start will be explained in detail later on. The starter-generator connection is controlled by the Associated Generator Control Unit, GCU. GCU function will be explained in detail at a later stage. During startup, the associated start on light illuminates on the engine start panel until the engine is cranked to the point where it's running on its own. When reaching 45% NH, which marks the end of the starting sequence, the starter generator is disconnected from its power supply and the associated start light extinguishes. Note, experience has demonstrated that if the gust lock is not properly engaged, and as soon as one of the start positions is selected on the engine start rotary selector, the starter generator 2 fault light is illuminated on the engine start panel. Despite the fault light, the crew is still able to start engine number 2. The starter generators, which are long-life brush air-cooled type, are rated to deliver a nominal output power of 12,000 watts, 400 amps without time limit. Consult the table for information about loads and associated time limits. The nominal output voltage amounts to between 27 and 31 volts, whereas the nominal setting is 30.0 volts. The generator mode engages when the engine reaches 61.5% NH, the associated DC gen push button is depressed, and the external power push button on the main electrical power panel is not selected on. The generator then feeds the associated DC bus. Connecting the starter generator to the respective DC bus is also performed by the Associated Generator Control Unit, GCU. Before we look at the cross start, it's important to first understand the following. 1. At the moment the engine start push button is depressed, a very high current, approximately 1,200 amps, is necessary to initiate the start sequence. 2. The main battery is able to supply 43 amps in 1 hour. But within a very short period of time, some milliseconds, this capacity becomes much higher and sufficient for the engine start sequence. 3. On the other hand, the maximum output of the starter generator is 800 amps during 8 seconds, which is not enough for the engine start sequence. This tells us that it is impossible to start an engine using only the opposite generator or without a serviceable main battery. Once one engine is running and the respective generator is connected to the DC electrical network, meaning that the external power unit, if used before, is disconnected, the other engine start is performed as a cross start. The cross start always begins with the main battery, which is the only source of electrical power supplying the starter generator until the engine reaches 10% of NH. From this point on, the operative generator will assist the main battery until the start sequence is completed. This assistance does not mean that the generator will take over from the main battery, but it will keep charging the battery. Be aware that the cross start is only available on ground. In flight, the main battery performs the engine start without any assistance. If the operative generator fails to assist during a cross-start sequence, an amber cross-start fail light illuminates on the main electrical panel, followed by the master caution flashing light, electric amber light on the CAP, and a single chime. The purpose of the GCU, which is mounted in the electrical rack, is to monitor the so-called point of regulation, where the voltage is maintained constant as the load varies. It also provides fault detection and protection for over or under voltage, over or under speed, differential fault current, generator overload, power and fault current limiting, bus tie lockout, reverse current, and equalizing load in case of bus tie contactor failed closed. The bus tie contactor, BTC, is determined to automatically provide the connection between the two main DC buses in case one generator is inoperative. Control of the bus tie contactor, as well as control of the battery start contactor, load shedding, external power functions, DC service bus contactors, DC utility buses contactors, and DC ground handling bus contactors, is performed by a single bus power control unit, BPCU, installed in the electrical rack. When we discussed distribution, we return to what we briefly showed you at the beginning of the electrical system, the buses. The electrical system is divided into several buses which provide electrical power to the systems and is able to automatically disconnect buses or consumers from the electrical network in case of malfunctions. A part of that, the electrical system is also able to switch buses or consumers to an alternative supply when necessary. Before we go further into the ATR electrical system, it's important to understand the Bus Power Control Unit, short BPCU. The BPCU can be considered the brain of the electrical system. It is responsible for controlling the opening and closing of the electrical contactors in both normal and abnormal situations. The target is to allow the load shedding and the reorganization of the electrical network in order to keep as many buses as possible energized. To manage the DC power supply, 11 different buses are merged to a hierarchically structured network. There are two main buses, DC Bus 1 and DC Bus 2, that directly or indirectly supply hot main battery bus and hot emergency battery bus, DC emergency bus, DC essential bus, and DC standby bus, utility bus 1 and utility bus 2, DC service bus, and ground handling bus. Note: consult the EFCOM Electrical System Distribution for a detailed list of the equipment supplied by each bus. The two main buses in the hierarchy, DC Bus 1 and DC Bus 2, are under normal operating conditions supplied by the engine-driven generators. DC Bus 1 is supplied by the left-hand engine-driven generator, and DC Bus 2 by the generator driven by the right-hand engine. If one of the DC generators fails, the bus power control unit automatically closes the bus tie contactor, allowing the affected DC bus to be supplied by the operating generator. This event is indicated by the illumination of the green flow bar in the normally released bus tie contactor push button on the main electrical power panel. You'll hear more about this panel in upcoming lessons. Here's the normal assignment of the buses. DC Bus 1 supplies hot emergency battery bus, DC emergency bus, DC standby bus, utility bus 1, inverter 1, DC service bus. DC Bus 2 supplies hot main battery bus, DC essential bus, utility bus 2, inverter 2. Now let's proceed to the hot buses. We start with the first subgroup of buses, the hot battery buses. Hot means that the respective bus is permanently powered regardless whether or not the main battery switch is selected to off. Both the hot main battery bus and the hot emergency battery bus are directly connected to their associated battery. In normal conditions with at least one DC generator operative, the DC buses feed the hot battery buses, and the hot battery buses charge the respective battery. Now let's proceed with the buses supplied by the hot battery buses. In normal operation, if the batteries are the only source of DC power, such as when powering up the aircraft without using an external power unit or the hotel mode, the hot main battery bus supplies the DC essential bus and the DC standby bus, and the hot emergency battery bus supplies the DC emergency bus. As soon as an external power unit is connected to the electrical network, or at least one DC generator is operative, the DC standby bus electrical power supply is transferred to the hot emergency battery bus. The same happens during engine starts. With both engines running, in case both DC generators are lost and the TRU is inoperative, the main battery supplies the hot main battery bus, DC essential bus, DC standby bus, and inverter 1, whereas the emergency battery supplies the hot emergency battery bus and DC emergency bus. If the same happens with an operative TRU, the TRU supplies the DC emergency bus, DC standby bus, DC essential bus, and inverter 1 without time limit, whereas each battery supplies the respective hot battery bus. When on battery supply only, if the DC standby bus comes into undervoltage condition, normally because the main battery is weakening, it will be indicated by the amber undervoltage light in the override push button located on the main electrical power panel. The DC standby bus and the inverter 1 can be transferred to the hot emergency battery bus by depressing the override push button. Now let's assume that both DC generators are operative. If one of the batteries has a thermal runaway condition, the buses connected to the failed battery are automatically transferred to DC bus 1. If DC bus 1 is not powered for any reason, the buses will be automatically transferred to DC bus 2. Supplied with DC power from the associated main DC bus, the utility buses 1 and 2 power only non-essential consumers. You've already learned that the bus power control unit controls, in addition to other functions, load shedding. This functionality takes effect in case one of the utility buses gets into an overload condition. In this situation, the BPCU will de-energize the affected bus. Two power sources are dedicated to providing the DC service bus consumers with the power needed in flight or on ground during aircraft servicing operations. In flight, power is provided by DC bus 1 when the DC service utility bus push button, located on the main electrical power panel, is standard depressed, and the DC ground service bus push button on the cabin attendant panel is also standard depressed. On ground, even with batteries switched off, an external power unit can be used to sustain the DC service bus functions. In this case, only the cabin attendant's push button has control of the DC service bus. Let's take a minute to understand how the DC service bus can be lost and what you can do to recover the bus. If the bus power control unit detects an abnormal operation of the DC service bus, for example a faulty relay, it automatically sheds the bus. The supply of electrical power on ground during aircraft servicing is the duty of the ground handling bus. The ground handling bus provides the electrical power requested by its consumers, regardless of the position of the battery switch on the main electrical power panel, even with the batteries off. The ground handling bus can be supplied from the DC service bus if an external power unit is available. If an external power unit is not available, the hot main battery bus supplies the ground handling bus as soon as the rear entry door, the cargo door, operating panel door, or the refueling panel door is opened. This bus provides the necessary electrical power for the cargo door and the refueling system operation. Note that if you have the choice, always use an external power source in order to avoid depleting the batteries. After takeoff, since the loads supplied by the ground handling bus are not required in flight, the bus is automatically de-energized. If no ground external power unit is available, the ground handling bus draws the voltage from hot main battery bus. This is indicated by illumination of the red light on the cargo door control panel, visible even when the access door is closed. Caution: the illuminated red light on the cargo door control panel indicates that, despite the battery toggle switch in off position, the main battery is emptying. The only way to avoid this situation when the aircraft is left unattended on the ground for long periods is to manually pull the associated ground handling bus circuit breakers located behind the co-pilot's seat. What can be the consequence of weak batteries? The DC generator load limitation of 600 amps for 2 minutes may be exceeded immediately after you start engine 2 with a weak battery. This will be caused by the charge current, which alone may reach 300 amperes and result in automatic protection engagement in the shape of shedding of DC service and utility bus, opening of DC bus tie contactor, and therefore loss of DC bus 1. DC generator 2 isolation, causing loss of DC bus 2. By taking the following actions after starting engine 2, you can prevent the previously mentioned disconnections from occurring. Monitor DC generator 2 load on captain's lateral maintenance panel. Switch off the following equipment as required in order to maintain the DC generator 2 load within limits. DC service and utility bus. Left-hand fuel pump. Both recirculation fans. As charging current decreases and consequently DC generator load reduces, you may bring the previously disengaged equipment back online. You've almost finished the behind-the-scenes basics of the DC electrical system. Before we look at how to control the system, let's see the basic logic again. When all push buttons and switches on the main electrical power panel are left in their normal position, the transfer of the DC power to the various buses is automatically performed by the BPCU by opening and closing the electrical contactors. The status of each contactor is determined by the particular electrical condition, which may be: in flight, when both engine-driven DC generators are operating, DC generator 1 supplies DC bus 1, DC generator 2 provides power to DC bus 2, and the bus tie contactor stays opened. In flight, when one of the starter generators fails, the bus tie contactor automatically closes, and thus the entire DC network is provided with electrical power from the remaining DC generator. DC power transfer on ground works the same as in flight, as long as no ground external power is connected to the aircraft. In this chapter, you'll learn about the controls and indications for the DC electrical power. Take a look at the control panels on the screen. We'll focus on the main electrical power panel in this lesson. The left lateral maintenance panel and cabin attendant panel with their controls and indications will follow in separate lessons. The electrical system controls can be divided into controls governing generation and controls over the distribution of power. Let's start with the power generation controls, which can be divided into main and secondary controls. You can find the main controls on the main electrical power panel, located on the overhead panel in the cockpit. There are the DC Generator 1 and DC Generator 2 push buttons, the external power push button, the DC service utility bus push button, the bus tie contactor push button, and the cross start fail light indicator. As we saw earlier, the cross start fail light illuminates amber if a failure is detected during the cross start procedure. Remember that it's available only on ground. The DC Generator 1 and DC Generator 2 push buttons are the main elements on this panel. These push buttons control the energization of the respective generator and permit a manual reset after a failure has occurred. The generator push button is in normal position, depressed and dark. This signals the generator control unit to connect the generator to the electrical network if the parameters of the network are normal and when the associated engine is running. Located above the DC Generator 2 push button is the standard released and dark bus tie contactor push button, which is protected by a spring-loaded guard. In released position, the bus tie contactor is automatically commanded by the bus power control unit according to network situation, which results in one of the following. Under normal operating conditions, which include both engine-driven DC generators operative, the bus tie contactor is commanded open, and each bus is supplied by its associated generator. If a DC ground power unit is connected, hotel mode is used, or only one generator is operative, the bus tie contactor is automatically commanded to close. This situation allows both DC bus 1 and DC bus 2 to be supplied either by the DC ground power unit or the operational DC generator, and is indicated by illumination of the green flow bar in the bus tie contactor push button. The external power push button, located next to the DC Generator 2 push button, in its normal released position is dark. When a DC ground power unit of acceptable quality is connected to the ATR, and all conditions for this connection are met, the green available light illuminates in the push button. Note that the bus power control unit is responsible for checking the quality of the DC ground power unit and for allowing its connection to the electrical network. To supply the system from the ground power unit, you need to depress the push button, whereas the blue on light illuminates. Detailed information about external power will be presented in a separate lesson. Located next to external power, you find the DC service utility bus push button, which permits you to manually disconnect the DC service bus and the utility buses 1 and 2, and also provides a visual indication if the buses are automatically shed by the system. In the normal depressed position, the push button is dark, and all 3 buses are available for their consumers as long as the bus power control unit has no reason to disconnect them. If a malfunction in the electrical system forces the bus power control unit to shed at least one of the utility buses from its associated main DC bus, the amber shed light illuminates in the push button and the CCAS is activated. Note that even if only one of the three, Utility Bus 1, Utility Bus 2, or DC Service Bus, is affected by a malfunction, all three buses are shed by the system. We've talked about the existing buses and how they're connected to or isolated from the electrical network either manually or automatically. We've looked at the main generation controls located on the main electrical power panel in the cockpit, but now let's look at the DC ground handling bus controls. The controls to power this bus, in case no ground power unit is available, are micro switches that check the position of doors and covers on the outside of the ATR. These switches are located at the rear entry door, at the refueling panel, and also at the cargo door operating panel covers. As you open one of these panels or the rear entry door, the ground handling bus is connected to hot main battery bus. The controls and particular indications for the distribution of DC power are located in the upper part of the main electrical power panel and consist of the DC bus 1 and 2 off indications, the main and emergency battery charge push buttons, the battery's toggle switch, the TRU push button, the emergency supply indications, the override push button, the DC ampere indicator, and the battery's ampere reading selector. The DC bus 1 off light and the DC bus 2 off light illuminate amber when the respective bus is de-energized. If one DC bus is not supplied, the CCAS is activated, a single chime generated, the amber master caution flashes, the amber electric light illuminates on the CAP, and the amber DC bus off light illuminates. Located directly above the DC bus off indications, the main and the emergency battery charge push buttons permit control of the associated battery charge contactor. The normal depressed position of the push button shows no indication and allows the MFC to control the associated battery charge contactor. The battery charge contactors are in normal position closed and automatically open if either an incipient thermal runaway of the related battery is detected, an undervoltage of the supplying main DC bus is detected, or when the battery toggle switch is set to override. The battery charge contactors are also forced open during the engine start sequence and are automatically closed again when start rotary selector leaves either the start or the crank position. The guarded battery toggle switch on the main electrical power panel has three positions: off, on, and override, which permits you to connect the main and the emergency batteries to the DC electrical system. The normal position of the battery toggle switch when you enter the ATR cockpit for flight preparation is off. This position causes isolation of all associated buses from the hot main battery bus and from the hot emergency battery bus. Once the battery switch is selected to the on position, the main battery supplies the DC essential bus, the DC standby bus, and the AC standby bus via inverter 1, while the emergency battery provides power supply to the emergency bus. During normal operation, the battery toggle switch remains in the on position. In this case, two electrical situations may occur. 1. On ground, when no electrical power is provided by the DC generators 1 and 2, or by a ground external power, the supply chain stays the same as stated before. 2. The situation changes if at least one DC generator or the ground power unit provides electrical power, and the respective controls are set in their normal positions. In this case, the DC standby bus is automatically transferred and powered by the hot emergency battery bus. The automatic transfer is commanded by which electrical system component? The bus power control unit, the battery charge contactor of the main battery, or the generator control unit of the operating DC generator. In case of a dual DC generator loss, if required by a checklist contained in the QRH, the battery toggle switch can be set to the override position. To select the toggle switch to override, you have to first lift the guard. This action overrides all protection functions of the electrical system and ensures that the buses are supplied by their respective battery in the same way it happens when no DC generator or external power unit are available. Note: do not confuse the override position of the battery toggle switch with the override position of the override push button that will be explained after this lesson. In the middle left side of the main electrical power panel, you find the TRU push button. In its normal released position, if one DC generator fails, the DC emergency bus and standby bus are supplied from the hot emergency battery bus. Furthermore, DC bus 1 supplies the inverter 1, and the hot main battery bus supplies the DC essential bus. In case both DC generators fail, the hot emergency battery bus supplies the DC emergency bus, and the hot main battery bus supplies inverter 1, DC standby bus, and DC essential bus. Once the push button is depressed, the TRU is connected to the AC wild bus 2. In this situation, the on light illuminates white and the arrow illuminates amber, indicating that the TRU is supplying the DC emergency bus, DC standby bus, DC essential bus, and inverter 1. In the center of this part of the main electrical power panel, you'll find the emergency supply indicator. There are two arrows in this indicator. The illumination of the right amber arrow informs you that the DC essential bus is directly powered by the main battery, and the illumination of the left amber arrow informs you that the DC emergency bus is directly powered by the emergency battery. Normally, both arrows will illuminate in case both DC generators are lost, and the batteries become the only DC power source available. If one or both arrows illuminate with at least one DC generator operative, it indicates that the respective battery is being discharged due to an internal system failure. Remember that the battery supply is limited to 30 minutes. In this situation, the CCAS is activated, illuminating the respective amber arrow on the overhead panel and generating the amber master caution flashing light, the amber electrical light on the CAP, and a single chime. Note that the MFC 1B or 2B controls the activation of the master caution, the electrical light on the CAP, and the single chime. These alarms are inhibited on ground or in case of a dual DC generator loss, or when selecting the battery toggle switch to the override position. Located directly above the emergency supply indicator is the guarded override push button. The normally released position of the push button shows no indication. In this case, the DC standby bus and the inverter 1 are powered by the same source as the DC essential bus. That is, by the DC bus 1 if at least one DC generator is operative, or by the main battery if no DC generator is available. You've already seen in which situations this control element has to be used. Remember the buses and their malfunctions. In case the batteries are the only DC power sources available, and when the voltage provided via DC essential bus to DC standby bus falls below 19.5 volts, the amber undervoltage light illuminates in the override push button. In this situation, and when required by a checklist in the QRH, you can open the spring-loaded guard and depress the push button. This action will illuminate the white override light. The battery ampere indicator and the related battery reading selector complete the controls and indications for DC on the main electrical power panel. These two allow you to check the actual current situation of the batteries. Selection of the battery that you want to check by using the ampere meter is done via the battery reading selector. The readout on the left half of the battery ampere indicator shows the actual discharge current, while the right half displays the charging current of the respective battery. The scale indicates amperes times 100. You've now completed the controls on the main electrical power panel concerning the DC electrical system. The DC electrical system of the ATR 72 not only generates and supplies power, but also controls the distribution and the indications. The elements involved in control and indication also need DC power to perform their job. Roll over the highlighted elements now to learn about how some of these controls and indications are electrically supplied. For a complete list, refer to the FCOM 1 electrical system. Now let's find out more about the possible electrical conditions and situations that provoke alerts. If there's a malfunction in the electrical system, the centralized crew alerting system will present you with information about the problem. The master caution amber light and the single chime are used to draw your attention to the alert. The crew alerting panel informs you that the electrical system is the origin of the failure. In addition, the local alerts on the main electrical power panel further provide a clear identification of the fault and direct you to the corrective action. Note: in case of a malfunction of the electrical system during aircraft operation, consult the ATR Quick Reference Handbook for the appropriate emergency procedures or procedures following failures checklist. We will first examine the alerts for DC generation and the main DC buses. In case a DC generator fails due to a malfunction, the CCAS is activated, the amber master caution light flashes, a single chime is generated to get your attention, and the amber electric light on the CAP informs you that the failure comes from the electrical system. Finally, the DC generator amber fault light of the failed channel identifies the failure and directs you to the appropriate corrective actions. If DC bus 1 or DC bus 2 is no longer supplied, the CCAS is activated, the amber master caution light flashes, a single chime is generated on the CAP, and the amber electric light comes on. At the same time, the respective amber DC bus off local alert on the main electrical power panel identifies the failure. Note that some other indications, such as the associated DC generator fault light, the associated inverter fault light, and the DC service utility bus shed light, illuminate on the main electrical power panel as a consequence of the main DC bus failure. The following alerts concern the main and/or emergency battery or their respective charge contactors. Either a thermal runaway of one of the batteries or a failure of one of the battery charge contactors will cause the activation of the CCAS, resulting in the flashing of the master caution light, the generation of a single chime, and illumination of the amber electric light on the CAP. Simultaneously, the amber fault in the respective battery charge push button comes on to provide detailed failure information. Now let's see some particular electrical situations and the alerts related to the DC emergency bus, DC essential bus, and utility bus. If, due to a system malfunction, the DC emergency bus is powered by the emergency battery instead of a DC generator, the CCAS is activated, the amber master caution flashes, a single chime is generated, and the CAP displays the amber electric light. Also, the left arrow illuminates amber in the emergency supply indicator. This situation alerts you that the emergency battery is being discharged. If a similar situation occurs involving the main battery, the CCAS is also activated, but the right arrow illuminates amber in the emergency supply indicator. This situation alerts you that the main battery is being discharged. If one of the utility buses has been shed by the bus power control unit due to an overload condition, the CCAS presents you with the following information. The master caution light flashes amber, a single chime is generated, and the amber electric on the CAP leads your attention to the electrical system. Detailed fault identification is provided by the amber shed local alert on the DC service utility bus push button. In the following lessons, you'll be introduced to the electrical AC constant frequency system. Two static inverters, single-phase type with a nominal power of 500 volt ampere, are the source of the AC constant frequency. They are mounted in the electric rack and cool by air. For the AC static inverters to operate properly, the main DC buses have to deliver a voltage between 18 volt DC and 31 volt DC. If one of the main DC buses is lost, the associated inverter, and by consequence the associated buses, are no longer supplied. When this happens, the bus tie relay automatically closes and supplies the affected AC buses with voltage from the remaining inverter via its associated buses. If the remaining DC bus also fails, the inverter 1 will be supplied by the hot main battery bus or by the hot emergency battery bus in case the override push button is depressed, or by the TRU when selected on. The override function will be explained in detail when we discuss the controls for the AC constant frequency system. You already know that two different AC constant frequency voltages are provided, so let's now follow their paths to the respective consumers. In the schematics we've seen so far, there was just one bus. However, both are 26 volt AC and 115 volt AC. The same logic applies, and the main electrical power panel shows just one bus representing both networks. Under normal operating conditions, the job of inverter 1 is to supply AC buses 1 and AC standby buses, whereas the static inverter 2 powers AC buses 2. The main electrical power panel provides you the main controls and indications concerning the AC constant frequency system. Further indications on the lateral maintenance panel will be explained in a separate lesson. In the center of the panel you find the guarded override push button. If at least one DC generator is operative, or a DC ground power unit is connected to the electrical network, The push button, in its normal released position, will allow inverter 1 and the AC standby bus to be supplied by the same source as DC bus 1. If the batteries become the only DC power source available, and by consequence both main DC buses are de-energized, both inverter 1 and AC standby bus will be automatically supplied by the hot main battery bus. If the voltage of DC standby bus falls below 19.5 volts, the amber undervoltage illuminates in the right half of the push button. This situation also concerns the AC system because the static inverters need a minimum of 18-volt DC for proper operation. If required by the QRH checklist concerning this situation, you're allowed to open the spring-loaded guard and depress the override push button. The guarded bus tie contactor push button is responsible for the control of the AC bus tie relays. In its normal released position, the bus tie contactor push button allows the bus power control unit to automatically control the position of the AC bus tie relays according to the actual electrical situation. Under normal operating conditions and with both static inverters operative, the bus power control unit commands the AC bus tie relays in the open position, and the networks of the two inverters work isolated from each other. In case one inverter fails, the bus power control unit automatically commands the respective AC bus tie relay to close, and the remaining inverter provides the affected buses with electrical power. The main electrical power panel is fitted with 4 amber lights to indicate a failure of the static inverters or the main AC buses. The inverter fault lights indicate a failure of the inverter 1 and/or of the inverter 2, while the bus off lights indicate that the AC bus 1 and/or AC bus 2 are de-energized. If an inverter fails, or if the DC power supply of that inverter is lost, or an under or overvoltage situation at the output of an inverter is detected by the system, the CCAS will be activated. The master caution light flashes amber. A single chime is generated, and the amber electric indication illuminates on the CAP. Initially, only the bus off light on the main electrical power panel will illuminate. After approximately 10 seconds, the bus off light extinguishes and the inverter fault light illuminates to provide the correct failure indication. This situation occurs because the bus tie relays take some time to connect the de-energized AC buses to the operative AC buses. Note: slight differences might be found in the FCOM describing the function of this system. The information given in the CBT is correct and corresponds to the function of the system in the aircraft and in the simulator. A second configuration of these two indications is presented to you when the respective AC buses are de-energized for any reason without a failure of the respective inverter. In this case, the CCAS is also activated. The amber master caution flashes, a single chime is generated, the amber electric indication on the CAP, and the respective bus off light illuminates. Note: in case the AC electrical system suffers a malfunction during the aircraft operation, consult the Quick Reference Handbook for the applicable procedure. The ATR 72 components, controls, and indications responsible for the generation and distribution of the AC constant frequency power also need electrical power to perform their job. In contrast to the DC system, the AC system's components use both AC and DC power to ensure proper operation. See and hear now, by rolling over the highlighted elements, how some of them are electrically supplied. For a complete list, refer to the FCOM 1 electrical system. Two types of AC voltage are provided for the various consumers of the ATR 72. One is AC of constant 400 Hz frequency, and the second is AC wild frequency that will be presented in this chapter. Why is it called wild frequency, and how is it different than AC constant frequency? Let's repeat. The AC constant frequency is served by two static inverters that regulate the frequency to 400 Hz. In comparison, the AC wild system sources are two three-phase brushless air-cooled type generators. They're attached to their respective propeller's reduction gearbox rear housing. Since they're driven by their respective propeller's reduction gear, the wild frequency of 341 Hz to 488 Hz results from the variations in the propeller's speed, from 70.8% up to 100% NP, while the aircraft is in flight. Each of the generators provides 115 volt AC and is rated to deliver 20,000 volt ampere for continuous operation. In this table you can find the load limitations of the AC wild generators, including the respective time limits. Let's now reduce the block diagram to the minimum logic, as it appears on the AC wild electrical power control panel. For distribution of AC wild electrical power, there are three buses. The two main buses, AC wild bus 1 and AC wild bus 2, and the AC wild service bus. Under normal operating conditions, each main bus is supplied by the associated AC wild generator. If we now assume that a generator fails, which action is automatically performed by the electrical system? Automatic reset of the affected generator to recover its function. Automatic closing of AC wild bus tie contactors to supply the affected bus from the remaining AC wild generator via the associated main AC wild bus. Automatic isolation of the failed generator and its respective main AC wild bus to avoid an overload on the remaining AC wild generator. Now let's look at the final component of distribution for the AC wild system, the function and supply of the AC wild service bus. The AC wild service bus not only provides its consumers with electrical power during flight, but also on ground during aircraft servicing operations. Energization of the AC wild service bus is controlled by the ground service bus AC push button, located on the cabin attendant's panel on the rear cabin wall. A more detailed explanation of this push button will follow in a separate chapter. The bus has two possible power sources, AC wild bus 1 or the AC ground power unit. The supply is accomplished by automatic connection to AC wild bus 1 when energized, either by the AC wild generator 1 or by the ground power unit via the bus tie contactor 1, or external power via a dedicated contactor if the AC wild bus 1 is de-energized or shed by the system. Note, if one of the generators is lost, the AC wild service bus is automatically shed by the bus power control unit. Located on the overhead panel, the AC wild electrical power panel provides the main controls and indications for the AC wild electrical system. At the left and right outer positions, you'll find the AC wild generator 1 and 2 push buttons for connecting and disconnecting the generators from the AC wild network. They're also used for manual reset of the protection system if a malfunction occurred. When the push button is selected on, standard depressed position, it's dark. and if all electrical parameters of the AC wild network are normal, the associated AC wild generator is automatically connected to the system as soon as the propeller speed reaches a minimum NP of 70.8%. Once the AC wild generator push button is selected to the off position, released, the respective generator is disconnected from the AC wild electrical network. This condition is indicated by the white off light illuminating in the push button. In case an AC wild generator fails, the respective generator control unit disconnects the affected generator from the electrical network and the CCAS is activated. The amber master caution flashes. A single chime is generated, and the amber electrical indication on the CAP indicates the affected system. This failure is identified in detail by the amber fault light in the respective AC wild generator push button. Note that in case the AC wild generator push button is manually selected off, the CCAS is also activated, but the respective fault light will not illuminate. If the failure was caused by an NP overspeed for less than 3 minutes, or a generator underspeed, reset of the protection system is carried out automatically. In all other cases, it is necessary to manually perform the reset by cycling the respective AC wild generator push button off and then on again. Located above each AC wild generator push button, the associated amber AC wild bus off light indicates that the respective bus is no longer powered. If this happens, the CCAS is activated and the AC wild bus off local alert illuminates. Located between the two AC wild generator push buttons, you'll find the external power push button. Its normal position is released. If an external power unit is not connected to the aircraft, no indication is displayed. If an AC ground power unit is connected to your ATR, the AC wild bus power control unit checks to see if the received electrical power is within limits. If all necessary conditions for the power supply are met, the green available light in the external power push button illuminates. The guarded bus tie contactor push button on the AC wild electrical power panel controls the AC wild bus tie contactors 1 and 2. The standard position of this push button is released, with no indications displayed. In this position, the AC wild bus power control unit automatically controls the position of both AC wild bus tie contactors according to the electrical system situation. If both AC wild generators are operative and all network parameters are normal, both contactors are in the open position and each AC wild generator supplies the respective buses. The AC wild bus power control unit commands both AC wild bus tie contactors to close simultaneously if the system is powered by an external power unit. The ATR 72-500 components, controls, and indications responsible for the generation and distribution of the AC wild power also need electrical power to perform their job. Similar to the AC constant frequency system, the AC wild system's components also use two types of electrical power, AC wild and DC, to ensure proper operation. By rolling over the highlighted elements with the mouse, you may see and hear how some of them are electrically supplied. For a complete list, refer to the FCOM 1 electrical system. If the AC wild electrical system of your ATR 72 detects a malfunction, it uses the following components to inform you of that occurrence. Initialized by the centralized crew alerting system, the master caution light and the single chime aural warning catch your attention for the initial acknowledgement of a failure. Then the failed system is identified by the respective indication on the CAP. To be able to react and to set the necessary corrective actions, the associated local alert on the AC wild electrical power panel provides you the detailed description of the failure. If one of the AC wild generators fails, the CCAS is activated and commands the amber master caution light to flash, a single chime to sound, and the CAP to display the amber electrical light for identification of the affected system. Finally, the amber fault light on the respective AC wild generator push button provides a failure description. The other possible indication is the illumination of the amber AC wild bus off light on the AC wild electrical power panel. If the associated main AC wild bus is no longer supplied with electrical power. Here the CCAS is also activated. The flashing amber master caution light illuminates, the single chime is generated, and the amber electric light on the CAP comes on. Note: in case the AC wild electrical system suffers a malfunction during aircraft operation, consult the Quick Reference Handbook for the applicable procedure. The ATR 72-500 DC and AC wild electrical systems can be supplied from ground power sources. To supply the respective electrical system, the appropriate ground power unit has to be connected to the corresponding external power receptacle. These connectors are located on the lower right side of the fuselage, just aft of the nose landing gear. Let's look deeper into the details of the external power system. When a DC ground power unit is plugged into the corresponding external power receptacle of your ATR 72, the applied external power has to be checked before connecting it to the DC electrical system. Which electrical system component performs this check? With the green avail light illuminated in the DC external power push button, and after selecting the battery toggle switch to on, you may depress the push button. Ground power units to be used on the ATR 72 are subject to particular specifications. These units have to be able to provide a steady current between 300 amp to 400 amp under 28 volt DC to ensure proper operation of all DC equipment prior to engine start. At engine start, the GPU must assure an additional starter current of 1000 ampere while maintaining more than 12 volt, which means an instantaneous power of 16 kilowatts. Experience has shown that only a few so-called 28 volt DC GPUs are capable of providing this amount of electrical power. Above the DC external power indications, you'll find an interphone jack and a pilot call push button. With a headset connected to the interphone jack, the ground technician can communicate with the cockpit crew. By pressing the pilot call push button, the CCAS generates a doorbell signal in the cockpit. The blue call light on the mechanic push button illuminates on the calls panel located in the overhead panel. Let's continue with the functions of the AC external power receptacle panel. The white AC connected indication on the left side of the panel illuminates when an AC ground power unit, delivering electrical power of acceptable quality, is connected to the respective receptacle. The AC power not used light illuminates when an AC ground power unit is connected to the aircraft and the AC wild service bus is not used. Below the two indicators we looked at earlier, you'll see the nose landing gear service light toggle switch. This switch allows operation of the service light located in the nose landing gear bay. In the rear cabin area, directly above the cabin attendant seat, you see the cabin attendant panel. which also provides two controls for the electrical system of your ATR, the DC and AC wild ground service bus push buttons. In its standard depressed position, the DC ground service bus push button displays the green on light whenever a DC external power is connected and available, or the DC bus 1 is energized. If the push button is manually released, the DC service bus is disconnected from the available power source, the green on light extinguishes, and the amber shed light illuminates. During normal operation, if the bus power control unit sheds the DC service bus due to an overload condition, the amber shed light illuminates in the push button, and the green on indication remains illuminated as long as either a DC external power is connected and available, or the DC bus 1 is energized. The DC ground service bus push button on the cabin attendant panel controls the power supply to the DC service bus in two different ways, depending on the available power source. When the available power source is the DC bus 1, the DC service bus is only energized if the DC service and utility bus push button on the main electrical power panel and the DC ground service bus push button on the cabin attendant panel are both selected on. When an acceptable DC GPU is plugged into the aircraft but not selected on, the DC ground service bus push button directly controls the power supply of the DC service bus regardless of the DC service and utility bus push button position. In this case, if the DC ground service bus push button is manually selected off, the second electrical system control on the cabin attendant panel is the AC wild ground service bus push button. It connects the AC wild service bus either to a plugged AC external power source, if within the required limits, or to the AC wild bus 1 if energized. The standard position of this push button is depressed. The green on light illuminates whenever one of the power sources mentioned before is available. The pilot's lateral maintenance panel provides further control and indication elements related to the electrical system of the ATR. Because the rotary selector and the various indicators are provided for maintenance purpose only, they are guarded by transparent covers to avoid operation during flight. Let's now explore the control and indication elements on the pilot's lateral maintenance panel and their purposes. The control element on this panel, the rotary selector, allows the connection of particular pickup points of the electrical system to the various indicators. These pickup points are predefined for external power, generator 1 and 2, inverter 1 and 2, battery main and emergency. When generator 1 or 2 is selected, the respective DC generator is connected to the DC indicators, and simultaneously the values of the respective AC wild generator are displayed on the AC indicators. Let's start with the indicators. At the top left, the DC voltage indicator shows the voltage at the selected pickup point. If you've selected one of the batteries for readout, the normal reading without load is between 25 volt and 28 volt. And if a load is put on the battery, it is between 23 volt and 28 volt. The DC current indicator, DC amp, displays the current that is generated by the source you've chosen via the rotary selector. Under normal conditions, for each generator, less than 300 amps should be indicated. The AC load indicator normal reading for the selected AC source should be below 0.5. Its scale shows the load applied on the source in 100%. The frequency indicator, under normal operating conditions, should read 400 Hz plus or minus 5 Hz for the frequency of the AC source chosen via the rotary selector. And finally, the AC voltage indicator that shows the selected AC source's voltage, which normally should be 115 volts plus or minus 4 volt. For some aircraft systems and equipment aboard the ATR, you've already come to know which networks provide the electrical power needed for proper operation. For detailed lists of the systems and components which are supplied by DC bus 1, DC bus 2, hot emergency battery bus, hot main battery bus, DC emergency bus, DC essential bus, DC standby bus, DC service bus, DC utility bus 1, DC utility bus 2, DC ground handling bus, 26 volt AC standby bus, 26 volt AC bus 1, 26 volt AC bus 2, 115 volt AC standby bus, 115 volt AC bus 1, 115 volt AC bus 2, 115 volt AC wild bus 1, 115 volt AC wild bus 2, and 115 volt AC wild service bus. See the FCOM chapter Electrical System Distribution.